Okay, let's continue again. Okay, so we're discussing the circuit equivalency of the antennas. So we have here we can see here the power delivered to antenna for radiation, the power dissipated as heat, and because the antenna, it loses power, as we have seen in the previous slide, because it radiates and because it dissipates. And dissipation is traditionally called anything which is generated as, because of heat. Let's continue again. And now we have the maximum power is delivered in an antenna for radiation and dissipation whenever we have this conjugate matching. Conjugate matching, we see that the resistance of the antenna, it has to be equal to the resistance of the generator or the circuit which generates the signal. And wait a second, when we have conjugate matching, yes, and we should have also that XA, the reactance of the antenna, should be equal to the negative of the reactance of the generator. So this is something which is equivalent when you talk about the polarization vector of an antenna with an incoming wave. Okay, we said before that we should have the complex part should be a negative sign. This is also the same for the generator and the antenna itself. Now, whenever we have a power a conjugate matching, which would be the conjugate matching between one side of the circuit equivalent with the other circuit equivalent, where the first side it was a generator, the second side it was antenna, the power, it can be written as such. The power is equal to 1/2 voltage of the generator times the complex conjugate of the current of the generator, and we can derive like this. But one thing that we notice in this case, when we have the perfect matching, we observe that half of the power is delivered for dissipation and half is delivered for radiation. Okay, so that means that actually we care mostly about the radiated power, right? So we don't care, we should not worry too much that some power is lost on the way. So it looks like to give some power for the cell phones through an antenna, half of the power is immediately lost in the antenna construct design just because of the traditional expected losses. Okay, so again we see the same the same thing expressed again. Half of the power provided by the generator is dissipated as heat in internal resistance of the generator, and the other half is delivered to the antenna. This only happens when you have conjugate matching. Maximum delivered power, okay, this is just a summary again. The power by the generator is equal to the power generated because of heat and the power emitted or radiated. Here we see that since we are talking about the radiation losses and the powers, etc., and we are considering the impedance once again, we are just coming back just briefly to the discussion of the efficiency. We've seen the efficiency in the previous sessions of our class, where the efficiency it was equal to the radiation efficiency, and which are described by the ER, EC, and the ED. So let's move again. The discussion for the antenna and its load in receiving modes, it is equivalent to the discussion that we can have for the transmitting mode, which means that these equations that we are writing here for the transmitting antenna, because we have the power which is radiated or emitted or sent out, the same equivalency can be constructed also for antennas that don't emit, but antennas that receive. Okay, so let's go back here. One important parameter is that the input impedance of an antenna is a function of the frequency. So the antenna is matched to the interconnecting transmission line and other equipments only within a certain bandwidth. Okay, so the frequencies, components within a certain bandwidth, they can communicate well. The input impedance of an antenna, it also depends on other factors such as geometry, the method of excitation, and the proximity to the surrounding object. Because of the complex geometries, only a certain number or limited number of practical antennas have been investigated analytically. For other antennas, the input impedance can be determined experimentally. So now the analytical investigation of all of these parameters, it might be so complex, and the same way that we don't have an analytical solution, let's say to a differential equation. So let's say few percent of all the possible differential equations have an analytical solution. So if you want to integrate cosine with sine, cosine theta d theta, we can correctly integrate it, or you can solve a differential equation which includes these terms. The rest, more than 99%, we solve them using numerical approximations. So we can do something similar also in the case of antenna, or we can determine the relevant parameters experimentally. And most of the components, they are experimentally measurable using certain designs for the components that will match the values that we want to determine. And another thing that we can add here. Okay, so let's move here. So for the antenna efficiency, we have the radiation efficiency, and we have the efficiency is equal. It can be represented as the ratio of the power delivered to the radiation resistance to the power delivered to RR plus RL. So RL, it represents the losses or the resistances measured in ohm, represent the conduction dielectric losses. So we have all the losses that we can see in an antenna. They can be used to determine the efficiency. Now, the horn antenna, this is the antenna which can transmit or receive let's say a signal or a wave, and the circuit equivalent is as shown here in this figure. Now, whenever we have, so let's say for antenna components, we first try to mention or to repeat something which are used, we have seen it a lot. So the resistance for any piece of wire, it is described as 1 over sigma times the length of the wire divided by the cross-sectional area. This is for DC applications. Now, for antennas, we have high-frequency applications, and whenever we have high frequency, the resistance, it can be described with this expression which is shown here, which is that the RHF is equal to the conductor surface resistance times the length divided by the perimeter of the cross-section. So this is, we can see that even in the DC application, the resistance is mostly the function of the geometric size of the resistance or other components. The same thing, it is also for the capacitors. So capacitors, the capacitance of a capacitor, it's always directly related to the geometric size of these components. The same thing happens also for the antenna. Now, this node, you can have a look. If the skin depth of the metal is very small compared to the smallest diagonal of the cross-section of the rod, the current is confined to a thin layer near the conductor surface. So we have the components of an antenna, they are conductors, but most of the time the skin depth is very small, which means that the antenna, because we know that inside the conductor, the electric field and the magnetic field components, they are all zero. We do remember this one from the electromagnetic wave discussion, when we had, for example, the reflection from a conductor or the reflection from, let's say, from an insulator. And as a reminder, we also remember that any component which has a non-zero conductivity, then we have a certain skin depth, because the wave intensity, it will be attenuated very fast, because the conductivity, it will create or induce an attenuation constant alpha, and this is also happening in these components of the antenna. They are conductive. Skin depth is very thin compared to the complete size of the antenna, which could be as large as this one. But this means that since this is a conductor, the current will only flow through the surface, and that's why we determine the conductor surface resistance. We don't care what is the total resistance. Anyway, the wave, it will not propagate into the conductor, it will reside too small content on the surface. That's why we see these values here, or at least that's why we call it RS. So now we remember what good conductors used to be. Something can be called a conductor, a good conductor, or a poor conductor, not only looking at the conductivity value, not only at the sigma, but we have to divide it with it as a function by the frequency, because being conductor or not conduct, a good conductor or a poor conductor, it's a function strictly of the frequency that we are using or that we are communicating with. Now we have also the surface impedance, which is shown here, ZS, and ZS can be described for good conductors as shown in here. And we can see that the resistive component and the reactant component, they are equal in magnitude. And this is equivalent to what we have seen for the impedance in the electromagnetic wave theory, where alpha was equal to beta. And beta, it had the complex part, alpha, it was the attenuation constant. Here we have an example. We have a resonant half wavelength dipole made of conductive material, which is copper. And the question is to determine the conduction dielectric efficiency of the dipole antenna at this specific frequency, which is 10 to the power 8 Hertz. If the radius of the wire, it is 10 to the power minus 4 times lambda. And the radiation resistance, it is 73 ohms. Okay, so that's the problem. And we have here the frequency is 100 megahertz, which makes 10 to the power 8 hertz. We have the conductivity value, we have the B, and all the relevant quantities. Now, since we have the frequency, which is 10 to the power 8 hertz, we have the speed of light divided by 10 to the power 8 hertz. We find the wavelength, which is 3 meters. The example we did in the previous session, not example, but what we wrote on the board, we had 1 gigahertz of communication frequency, and we found that the wavelength, it was 30 centimeters. So it's something like this. This is 1 gigahertz. Length scale is this large, around 30 centimeters. But if it is 100 megahertz or 0.1 gigahertz, we're talking about for wavelength, which is 3 meters. The half wavelength dipole, the L, will be half of the 3 meters. It will be 1.5 meters. And also, in this case, for the half wavelength dipole antenna, the RL, it is equal to half of the high frequency resistance. So this is also which you can consider this as a given. And we just move ahead. So if the RL, wait a second. So we can determine the RHF, and RHF, we can use this expression, which is given here, which is L divided by P times the frequency of omega. Now this omega, it is going to be 2 pi f, which is 2 pi times 10 to the power 8, times the permeability divided by the conductivity. So this expression that we see here, we just substitute all the values, and we find, in fact, the C is a perimeter, which is 2 pi b, Dupuytren of any circle. We find the RHF, we find the RL, and the efficiency, it is going to be described by this expression, which is, I think it was a couple of slides before, but the efficiency is going to be something like 99.5%. In decibel, we notice that this is going to be in the order of, we have a very low loss, which is minus 0.02 decibels, because of this existence of 73 ohms. Now, another important parameter of the antennas is the vector effective length, and this is effective length of an antenna. It's a quantity which is used to determine the voltage induced on the open circuit terminals of an antenna when a wave impinges on it. When a wave is incident on an antenna, it has an important parameter, which is the electric field. If we multiply this electric field, actually I'm using this A4 piece of paper just to denote the relative size of the antennas, and a cell phone is also a very good equivalent when we discuss about the size of antenna components. So let's take the cell phone because we are more used to this one used as a communication device. So this is our antenna, we have an incident electric field, electromagnetic wave. We've talked about that the field, it can be in the order of 5 or 1 volt per meter. If we multiply this strength of electric field measured in volt per meter, multiplied by this length scale, we find the voltages. And but vector effective length is this one. Actually, when you say effective, it is very important whether the antenna, so if you have an incoming wave, it is essentially very different whether the antenna is standing like this or the antenna is standing like this. And we're going to see whether this is an important match, or it might cause, if it might cause any effective mismatch between the incoming wave and the antenna itself. A good vector effective length. The polarization efficiency, I think polarization efficiency, we talked a few in the first session that we covered today. We defined it as given in this slide, but we did not know what was the vector effective length as in the correct terminology. We just said that it was a length scale, so these are these values. Now, here we can see an incoming wave which is coming to a linear antenna, and the incoming propagation vector, which is shown in green, it has an associated electric field vector, incident electric field, which is perpendicular to this direction, and it is falling onto this antenna, which has a length scale L. But L is the antenna itself. We care about LE, which is the vector effective length, and the size of the antenna is not always equal to the effective length scale. So this would be the size of the cell phone depending on the angle. With respect to the incoming wave, the effective length scale, it can even be 0 or maximum. Now, the potential which is created at the antenna when an incident electric field wave is incident is equal to the integral of EdL. We should get, and the maximum potential that can be created at the antenna is Vt, denoted by the expressions here. And again, this is the same expression. The VOC, it is the open circuit voltage generated at the antenna terminals by an incident wave. So we have the incident electric field, we have the vector effective length, and the effective length represents the antenna in its transmitting and receiving modes, and it is very useful in relating open circuit voltage for the receiving antennas. Now, open circuit voltage can be thought as the voltage induced in a linear antenna of length L0 when L or LE when LE and the E are linearly polarized. The effective length of a linearly polarized antenna receiving a plane wave is defined as the ratio of the open circuit voltage to the electric field strength. Okay, so we're simply dividing the voltage to the electric field, and we know that when we divide a quantity which has units of voltage with another quantity which is measured in volts per meter, we're going to get meters. Okay. Now, the second sentence is more, well, it is slightly more intuitive. So the effective length is the length of a thin straight conductor oriented perpendicular to the given direction and parallel to the antenna polarization, having a uniform current equal to that of the antenna terminals and producing the same far field strength as the antenna in that direction. Okay. So so another thing that we can add here when we discuss the aspect of the effective length scale of antennas, we can say that in the far field region, the electric field, it can be described. Now we're discussing the parameters of the antennas. Maybe you are not very familiar looking at equation 2.92 and in terms of how the electric field looks when we are far away from the antenna, or when the electric field is expressed only as a function of A theta and A phi. But this is how an electric field looks like. And you have also this notice far field quantity of the E. And now vector effective length. The vector effective length, it can be also called the vector effective height. Now, it's a length scale, but we are assuming that this is also a height. it's not that different. And actually, this the length scale of the antenna, it is also analogous to the effective aperture. Effective aperture, I think we kind of mentioned this one before. We said that the antennas are not always as lines, but they can also be as apertures, where a horn antenna could be a very good example if we want to visualize it. Now, here we have an example. So we can have a far zone field radiated by a small dipole element given by a length scale, which is smaller than 1/10 of the wavelength, and it has a triangular current distribution as shown in this figure. Now, the antenna we're discussing, it is a dipole antenna. It has a geometry which is shown on the right side of the slide. And from the previous slide, what we want from here is that we want the expression of the electric field. So just looking at the slide for the expression of the E, we have, or at least what is given here, is that the electric field is given by this expression here, and we have to determine the vector effective length. And inside. So if we compare this expression of the electric field in this side with the electric field which is given here in green, you may notice that this one in this slide, it has extra components. It is L. For example, there is an L divided by 8 pi. Here, we just have the frequency, or the angular frequency, the omega, times the permeability, times the current in the antenna, times this exponential term. In this side, we have the current, the length scale, and the exponential term of the antenna. So it looks like this new expression, it has more components, which means that if we divide this EA given here with the EA given in this 2.92, we will find the effective length scale, which in this case is going to be L/2 times sine theta. And it looks also that the effective length scale, if this one is a function of angle theta, it is we can easily obtain a length scale, effective length scale, which can be also equal to 0 whenever. So, and also we have to notice where is the angle theta measured with respect to which direction. We notice that this angle theta is measured with respect to the z-axis. So for the maximum, it is when the wave is approaching at a direction which is 90 degrees with respect to the z-axis. Okay. Now we talked about effective length scale. We have also effective aperture, which now the similar discussion we had so far regarding the length scales will be done here for the apertures of antennas. Now, this is how the construct of an antenna can be. And this antenna, this is a linear antenna because, at least in this projection that we see, because the dimension is considered to be L. So that's what we pick out for the dimensions of the antennas. And we often compare the L with the wavelength with lambda. And we have here the propagation, the direction of the propagation of an incoming wave. We can also see the direction of the electric field, which is orthogonal with respect to the propagation. And here we see the previous image, which is slightly more visible. Apparently, this is how a receiving horn antenna is going to look like. So it has an effective aperture area where the wave will be incident. And the power delivered to the antenna, it is equal to the power density of the incident wave. And the power density, we know what it is. It is is proportional to the electric field squared. So if we know the electric field, we just calculate the square. There's a power density, and because it has units of watt per meter squared. So that's actually judging by the units of the quantities, it's always more relevant. So we just multiply it with the effective area, and we're going to find the total power delivered to a specific load. If we assume no losses, the let's say the area, it can be also described by the expression that we see here on the right side. We can also determine the aperture efficiency, and the aperture efficiency, it is given here as the ratio between the maximum effective area divided by the physical area. And this also means that the maximum effective area is going to be, which is also the aperture, the maximum it will be equal to the size of the antenna. So horn antennas, you can find them in the lab. They are something which could look, the common ones could look like half of this cell phone. So that means that the aperture or the area of the antenna is equal to 10 centimeters, or let's say 20 centimeters by 20 centimeters square. That would be the area. And we see some notes at the bottom side of the slide. So for aperture type antennas, which would be waveguides, horns, reflectors, the maximum effective area cannot exceed the physical area, which we mentioned this one. So for lossless antenna, the maximum value of the scattering area is also equal to the physical area. Therefore, even though the aperture efficiency is greater than 50%, for lossless antenna, under conjugate matching, only half of the power is delivered to the load. Now, here we are just going back once again, actually, to what are all the possible losses that can be in an antenna. So when we talk about the optimization or the design of an antenna, we have to consider, so actually we're kind of going back to every possible loss on this slide. So the first component is the effective aperture, which is lambda squared times d0 divided by 4 pi. And this is relevant because this is an area because it's proportional to lambda squared. The second component, it is the reflection coefficient, which is happening at the boundary between the transmission line and the antenna. And this reflection coefficient, this is, we know, we've seen this before, is just a loss, which means that from the generator through the transmission line, it will never make into the antenna to be radiated later on. And then we are including here also the efficiency, which comes because of the polarization mismatch or polarization match between the antenna and the wave. Okay, so derivation of effective. So we can derive, actually we have the equations or the relationships regarding the aperture of an antenna. So we can go over these slides, and actually we can also come close to the finalization of today's section. Do you have any question for what we are doing so far? If not, we can have a short break.